For the first talk in the afternoon session, we're very happy to have Henry Lin, who will tell us about algebra and geometry from Chords.
Thank you so much to the organizers. This talk will be based on a paper that I wrote in August, as well as some upcoming work with Douglas and Zenvin. Okay, so let's start with two equations. The first one equates the partition function of gravity with the partition function of quantum field theory. And the second one equates their Hilbert space. And wouldn't it be nice to have a microscopic derivation of these equations? By that I mean starting from just the UV definition of the theory and just doing some transformations without any input from knowledge about string theory. Now, that's a hard problem, and I don't know how to do it. I don't even know how to define the right-hand side in either of these equations, at least in some complicated models of holography. Okay. However, we can retreat a little bit from this problem and ask this question in SYK. And the reason why this is a retreat from the problem is because the first equation is already derived. So that's the famous G sigma action. And it's analogous to, let's say, the Einstein action, only in the sense that 1 over n appears in the same way that G Newton appears. You probably don't need to do that. Now, that motivates the question of whether we can understand the second equation in SYK. Right? The second equation is, in a large part, the topic of the It from Qubit. So one immediate idea is that you might think, well, let me just cut open the G and sigma action and use the path integral to define states, similar to how I would do it in a field theory. But this immediately runs into a problem, and the problem is that G and sigma are non-local. So this immediately fails. But there's a different limit of SYK called the double scale limit, which was analyzed by a lot of people, especially Berkooz and company, who developed a new technique for understanding SYK using these so-called chord diagrams. And using these so-called chord diagrams, we'll be able to make some progress in understanding the second equation. This is an interesting solvable limit of SYK that enhances certain quantum effects and suppresses other effects. So for example, the chaos exponent is finite in this model. So that's a bit like having stringy effects, perhaps, or sophisticated model. Okay, we can actually say a bit more about the bulk to boundary map, but instead today we'll be focused on an algebra of operators that acts on this Hilbert space, bulk Hilbert space, and we'll try to understand why there's a finite temperature Lyapunov exponent in a certain regime, as well as understand the bulk isometry. So what are the symmetries of the bulk spacetime from just a microscopic description of SYK. So let me start by a quick review of JT gravity. JT gravity is described by a particle and a potential. We heard a little bit about that in the last talk. And the idea is that the length of the particle, the length of the wormhole is described by the position of the particle. So if you know about particles and potentials, you know about JT gravity. Okay, so the fact that there's a potential that's e to the minus L explains why the wormhole grows, for example, at late time. Now, the classical motion just involves scattering off of this potential. So at early times, we start with a very long state. It reflects off the potential at t equals 0, and then goes back at very late time. And that's the classical motion. We can also continue at t equals 0 to the Euclidean signature. Okay, when we continue to Euclidean signature, we flip the sign of the potential, and the Liouville wall becomes a Liouville cliff. And that describes the thermal field double becoming ending at the bottom of the disk. Okay. Now, now that you know all there is to know about pure JT gravity in the gauge invariant formalism, classically, now we can move on to quantum mechanics. The quantum mechanical solution of this particle in the potential can be obtained using standard undergrad textbook methods. You get these scattering states. And we could say in pure JT gravity that the bulk Hilbert space at the level of the disk is just the span of these wave functions. Okay? So this is a two-sided bulk Hilbert space. And I emphasize that it is the Hilbert space associated with two entangled quantum mechanics. It is not the Hilbert space of the single quantum mechanics. And this is also another caveat is that this is without matter. So when we include matter, the story is much richer, and we'll discuss this later. Now, despite just saying that it's the two-sided Hilbert space, I will now say that you can compute the one-sided partition function of gravity using the two-sided Hilbert space. So how you do that is you use the observation that the disk has 2 points where the length between the two sides of the wormhole is 0. Okay? So those are obviously any 2 points, but for convenience, we can take them to be the south pole and the north pole. And then we write the disk partition function as an amplitude between the length equals 0 state at the bottom and the length equals 0 state at the top, using the Euclidean propagator. Okay, so as a simple exercise, you can use the eigenfunctions that I just showed in the previous slide to derive the sinh square root of E density of states that you're probably familiar with. Okay. Now, the reason why I'm reviewing this formalism in this particular way is that in SYK, all of the natural variables are gauge invariant. So you'll notice that I have not discussed the metric or the dilettante. And that's because to make connection with SYK, we need to talk about quantities that are intrinsically diffeomorphous and invariant. All right, now let's review double-scaled SYK. So this is the SYK Hamiltonian. The double scaling limit is Q goes to infinity, where Q is the number of fermions in interaction, and goes to infinity with this quantity lambda being held fixed. And there are two-dimensionless quantities in this theory. There's lambda, and then there's beta j. Okay. The standard large Q limit is lambda going to 0 with fixed temperature. That is the limit, for example, where the chaos exponent can be finite. So it can be maximal at very low temperatures, or it could be finite at higher temperatures. There's also the triple scaling limit where we send lambda to 0, beta j to infinity, holding this combination of quantities fixed. Okay, that's basically the inverse Schwarzschild coupling, and that in this limit we expect to recover JT gravity. Now, the observables in this theory were discussed by Berkooz et al., and they are these random operators. So I'm using a multi-index notation where psi is a product of fundamental fermions. Okay. And K here is a set of random couplings. So it's very similar to the Hamiltonian, except for these couplings K are independent of the couplings that appear in the Hamiltonian. Okay. So all the observables, including the Hamiltonian, are just random operators, random coefficients. Now, Berkooz and company have, in a series of remarkable papers, completely solved the model. And that means that they've computed the partition function and all thermal correlation functions. Okay, so the final answers in these papers involve these Q-deformed gamma functions. And given that they completely solved the model, you might wonder what else is there to talk about? Why am I talking right now? And the answer is that we want to understand their solution in a bulk language. So that's the main motivation for what I'm trying to do. Okay, so in order to explain the connection to the bulk language, I want to first review the computation of Z of beta. So the steps are actually extremely elementary. You can definitely follow it if you know just sort of basic quantum mechanics. And the idea is that you Taylor expand e to the minus beta h. You then focus on a particular term in the Taylor expansion. Okay, and a particular term, let's say h to the fourth, will involve some Wick contractions once you do the disorder after. Right? So you draw a bunch of Wick diagrams like you were taught, and the Wick diagrams just keep track of the indices that appear after you do the disorder after. Right? So here there's II and JJ. Okay, then to evaluate the trace that remains, you just use the Majorana algebra. So you just use the fact that psi I squared equals 1. So at the end of the day, this whole thing gives you either plus or minus 1, depending on the particular values of the indices. Okay? So whether you get a plus or minus 1 depends on whether there are an even number or an odd number of fermions in common between these two sets of indices. So the trick is that in the double scaling limit, you can forego keeping track of the exact plus or minus 1s and just replace that with the average value of the phase, plus or minus 1. And that can be computed easily, and it's e to the minus lambda. So the rule is that every time you see this Wick contraction, you just need to keep track of intersections and insert this factor of e to the minus lambda every time you move I past j, which is the same thing as having an intersection in the middle of this diagram. Okay, and then the final step is the sum over Wick contraction. So this can be summarized by a set of diagrammatic rules, and that's what the chord diagrams are. So the idea is that we sum over all chord diagrams, which are just, remember, the Wick contraction diagrams that you were taught to draw. And for each intersection vertex, we write down a factor of Q. So this is some particular contribution to the thermal partition function where there are 6 intersections in the book, so you get a Q to the 6. And the final trick is to figure out how to enumerate all possible chord diagrams. And we do this by using the transfer matrix trick that they introduced. Now, the idea is to make contact with JT gravity, we slice open the chord diagrams in some particular way. So given any particular chord diagram, you can find some location where there are no chords passing through this red slice. And then as we advance in either the left or right directions, we consider what happens when we insert a value of, when we insert H, the Hamiltonian. So that defines some transfer matrix. And as you can see, very suggestive that this equation is related to the equation that I wrote before in JT gravity. Now, this immediately suggests that the chord number plays the role of length in the double scale theory. And that's in fact correct. So the chord number is some discrete integer, whereas the length is a continuous variable, but in some particular limits, they're going to agree. Now, to make this more explicit, we need to work out the specific form of P. So in principle, we have two operators, the left Hamiltonian and the right Hamiltonian. Remember that this is a two-sided way of thinking about it. However, without matter, these operators are identical. And so we just need to consider, for example, the action of the right Hamiltonian. And the right Hamiltonian can do two things. It can either create a chord or annihilate a chord. If it creates a chord, that's accounted for by writing down this alpha dagger. If it annihilates a chord, well, it can either annihilate 3 chords like in the picture above, or it could annihilate 2 chords, or it can annihilate 4 chords, etc. So we need to sum over the number of chords that it passes through while it's being annihilated. And that is the sum here. That gives you what's known as a Q-deformed integer. It's just 1 minus q to the n over 1 minus q, but this thing is called the Q-deformed integer in the math literature. Okay, so that's the expression for the transfer matrix. If you then just solve the transfer matrix, as Berkooz and company did, you can work out the partition function and more properties of the system. However, we can also include matter, and the only minor modification is that the Feynman rules are modified so that you have black chords, which are the Hamiltonian chords, and these green chords, which represent these matter operators. And intersection vertices are modified so that instead of just having e to the minus lambda, you have e to the minus lambda times delta, for example, when there's a crossing between. And the fact that the thing that appears in the exponent is proportional to the masses or the sizes times the Newton's constant can think of as a 2D version of the Newton's. So the Hilbert space discussion in the case with matter is a little bit richer. So instead of just having one chord number, you actually have 2 chord numbers, for example, if there's one matter particle. So there's the number of chords to the left of the matter particle, this green chord, or the number of chords to the right. So then you have 2 kinds of creation and annihilation operators, alpha dagger right and alpha left. Okay, but you see that the structure is very similar. So again, acting with a right Hamiltonian, you can either create a chord or annihilate a chord. So the creation operator gives you this alpha dagger. The annihilation, now you can annihilate the right chord, or you can annihilate the left chord. If you annihilate the right chord, you just get a factor of this Q-deformed integer WR. And if you annihilate the left chord, well, you have this factor of Q to the n right, because you have to cross all possible right chords. Okay. So the summary is that you just need to know about some combinatorics in order to figure out these transfer matrices, and it's extremely elementary combinatorics. And for general states with m particles, you can obtain some expressions. The Hilbert space then involves m chord numbers instead of just 2 or 1. Okay. The only feature I want you to remember is that the right Hamiltonian only involves a single creation operator, alpha dagger right. You can only create a chord on the right using p right. It never creates a chord on the left, for example, or one in the middle. That was a convention that we used to define the transfer matrix, but it's going to be important later. Now, so far, I've only discussed a bulk vector space. So it's a span of a bunch of these vectors. In order to make it a Hilbert space, I need to specify the inner product. So the inner product will also help us facilitate contact with JT gravity. And it is simply defined by this equation. So the idea is that you view the overlap between, you view this transition amplitude as an overlap between states. Okay, and this gives you some equation for the inner product. Now, it's more illuminating to write that equation geometrically. And that equation says that you can split a general chord diagram into 3 regions, a bottom region which defines a ket vector, a top region which defines a bra vector, and some middle region which defines the inner product. The rule is that all chords entering the bottom of the middle region, so this line gamma n, must exit through the top. That defines the inner product. And using this definition, you can write down a recursion relation and in some cases solve it to obtain an expression for what the inner product is. Now, when you do that, you can use it to compute the P matrix now in an orthonormal basis. And when you do so, you get this expression. So this is some expression where I've defined a new variable L, which is lambda times n, and K is the momentum that's conjugate to L. Okay. So if you then take the triple scaling limit, which in this context means you take length to infinity, lambda to 0, but holding this quantity fixed, okay, you recover on the nose the JT Hamiltonian. Okay, so this is a microscopic derivation, let's say, of this formula. This was already, to some extent, pointed out in the Berkooz papers, but we can redo it now with matter. And what's interesting is, for example, with a single particle, we get these other expressions for the left and right Hamiltonian and the left and right lengths. We get some expressions which were not known even in JT graph. Okay. As you can see, the general case will give you some sort of scattering problem, but now instead of being a one-dimensional scattering problem, it's now some m+1 dimensional scattering problem, where you have m+1 coordinates corresponding to the various different links inside the work. Okay. Now, let me just comment now on the microscopic interpretation of the chord number. So in general, there's this notion of operator size. So you can take any two-sided state and expand it in the basis of fundamental fermions. And you can write the state in this particular form. So here C S sub I is the size wave function. And the size in general, which acts on the state by multiplication by S, is just accomplished by this operator here. Okay, so this is discussed in Stryker and Chi. And it's a very simple exercise to check that using this definition and the chord rules, that the size operator is actually given by n bar, so the total chord number, up to this factor of q. And this simply says that each of those open chords that we were cutting is an operator of size q, which of course makes sense, right? These individual operators are just Hamiltonians, and they are a product of few fermions. So it makes sense that you have this equation. Now, let me turn to the chord algebra. So the question is, what should I do with these expressions that I had for t left, t right, and n bar? Okay. So one thing you can do is just start taking commutators of things. And to motivate that, I should say that in JT gravity, we would like to in general, we would like to understand the symmetries of the bulk. That's sort of the 0th order question that you might want to know about in holography, right? What are the symmetries of ADS, for example, and do they match something in the CFT? So in ADS2 or nearly ADS2, that's actually a somewhat subtle question. So the gauge invariant symmetries, they do not commute with the Hamiltonian. So you need a slightly more complicated discussion, and that's what we're going to discuss here. So the way you get these symmetries is by essentially just taking commutators. So first thing that you can check is that the commutator between t left and t right is 0. That's completely obvious because because h left and h right act on different factors of the Hilbert space, but it's actually not obvious from the expressions that I wrote down. The expressions that I wrote down involve alpha dagger left and alpha dagger right and so forth, and it's actually non-trivial to check that that holds. But you can check that, and similarly, you can check all these other relations. Okay, now if you stare at this expression for a little bit, you'll recognize, if you read Harlow and Wu, that this is some sort of Q deformation of the JT gravitational algebra. So there's actually quite a lot of information in these sets of equations, and the rest of the talk will be trying to extract a little bit of this information from this algebra. Okay, so one thing that you can look for is the symmetries of the bulk. And how you find the symmetries is you look for operators in this algebra that commute with the chord number, the total chord number, which we interpreted as the length of the wormhole in the JT limit. So you can find 4 such operators, and you find them very simply. So alpha dagger left is part of the algebra, and so is alpha dagger right. Okay, they appear, for example, here. Right? And those create a single chord, right? So if you can multiply it by an annihilation operator, you could get something which does not change the chord number. Now, this is why you needed to remember that T left contained a factor of alpha dagger left, but no factors of alpha dagger right. So this expression T left minus alpha dagger left only contains annihilation operators. Okay, so these expressions are just one creation operator and some superposition of annihilation operators, so they manifestly commute with the total chord number. So these are four things. You can compute their algebra. But in order to compute their algebra, it's more convenient to first redefine them slightly by shifting away some function of the total length, which commutes with this, so it's allowed thing to do. And you can define h's then, which are just these rescaled versions of x. Okay, so now we can state what the result is for this algebra. It's given by these sets of equations. The quantity here, c, is just the exponential of the length. The length is defined by lambda times the coordinate. Okay. So you see that this appears in the algebra in some particular way, and we can simplify it a bit further by further shifting the definition of h. So we can actually eliminate c from the right-hand side of this equation by redefining h in some way. And the answer that we get is some subalgebra of this Q-deformed SL2 thing, which sounds pretty scary. Right? So my message now is not to panic. The only thing you need to know about this Q-deformed algebra is written by these three equations. So these are just four operators which satisfy these particular relations for our purposes. There's actually more structure to the algebra than these equations, but for our purposes, this will be enough. And there's E plus and E minus roughly become L plus and L minus in some limit. And the difference of this K plus minus 1 becomes L0. So you should think of this as just some deformation of the SL2 algebra. And this H algebra that I just mentioned, okay, becomes some subalgebra of this particular algebra. So let me repeat that just to be clear. So we do not in general find that the algebra is the quantum deformation of SL2. We instead find that it's some subalgebra of this SL2. And in order to identify the particular subalgebra, I've written the expressions. Okay, so let me just say that what we can start doing now is looking at the representations of this algebra. In particular, if we look at single particle states, so we had one chord in the wormhole and some number of chords to the left and right, we find unitary finite dimensional representations of the subalgebra. So this is a little bit funny because SL2 you think is a non-compact group. It does not have finite dimensional unitary representations, but this is some quantum thing, and you can actually very explicitly calculate and see that there are these finite dimensional representations of these particular objects here. And that makes sense. So since you're fixing the number of chords in the wormhole, you're just saying that there's like 3 chords, and the possible locations of the particle are limited, right? So this is a direct consequence of the fact that there is something discrete in both. Furthermore, we can find some Casimir, and that Casimir can be promoted to full Casimir of the algebra. Okay, so that was quite abstract. Now we can relax a little bit and discuss some more concrete things. So let me try to give you some feel for the algebra by focusing on a particular generator, which is this momentum generator. Okay, so it's the difference between HLR and HR. So first of all, this thing here, remember, it basically creates a left chord and annihilates a right chord. So this thing here is just a sort of discrete translation operator, right? It removes one of the left chords and puts it back on the right. So that moves the matter particle in the wormhole. Now, one question that you can ask is what happens as I act with this translation operator on a particle in the wormhole? So this is some finite space. Remember, there's only a finite number of chords. So what happens if I act with momentum in a finite space, right? It seems like a weird thing. And well, one proxy for that is to calculate the spectral form factor of this P operator. And what you see is that there's a recurrence. So that's what happened is you had the particle in the middle of the wormhole, let's say. You act with momentum, that translates it somewhere in the wormhole, and eventually it comes back to the middle. Somehow that is a symmetry of this bizarre limit to S like K. Now, furthermore, we can examine the microscopic expression for P. So the expression of P in terms of fundamental fermions. And to do that, we just translate all those algebra things into these concrete expressions involving the size operator N and T left and T right, which are the Hamiltonian. So this gives us some microscopic expression for, let's say, the generators. And we see that it's roughly speaking a commutator of the size with the t left minus t right. Okay, that's true in some particular cases. And in the particular cases which is true, we can use it to derive, for example, the Chi and Stryker formula for the growth operator size. So you can think of the growth operator size as a consequence of the Chord algebra. And that was known in the case of JT gravity, so at the very low temperature limit. But here we're showing it for finite. So the finite temperature growth of size, which is sub-maximal in general, is reproduced by this funny algebra. Okay, now we can play various games. So we can take various contractions of this algebra. So one thing that we can do is take Q fixed and n bar goes to infinity. So that's the limits where we're going to very low temperatures and we get a very long wormhole. Then this group contracts something and also take the limits where the length is fixed, but Q goes to 1. The frac Q goes to 1. That is the sort of standard SYK limit, remember. And then we can do both of them and then get the standard discussion of the triple scaling limit. So let's first start there where this discussion is most familiar, perhaps. So if we go all the way to the bottom right, we get the isometries of nearly ADS2, which are just the near horizon symmetries of a near extremal black hole. Here we've just constructed them explicitly. So the expressions for those generators, the boost, the momentum, and the global time translation are given by these microscopic expressions. Okay, they are gauge invariant symmetries. They move matter with respect to the Schwarzian boundary while leaving the length of the wormhole. Now, plugging in our triple scaled expressions for the left and right Hamiltonian, we can get some very concrete expressions for how they act, let's say, on a single particle. Okay, and the only important thing that I want you to know is that they act very concretely in terms of this variable x, which is the distance from the midpoint of the bifurcate horizon. Okay, so x is just the location of the particle, and these elementary expressions act on wave functions of x, and you can check in about 2 minutes that this algebra is satisfied with the expression. Now, when we include finite lambda corrections, this symmetry group gets deformed into the quantum group UQSL2. Okay, so the thing to say is that you get the full quantum group in this particular limit n goes to infinity. So we're now discussing the upper right thing where n bar is infinite, and in that limit you get the full quantum group. But when you get n finite, you do not get the full quantum. So that describes the low temperature but finite lambda symmetries of double-scaled SYK. And it's an interesting thing, this quantum group, because it has more structure than just the algebra. So it has this thing called it's actually a Hopf algebra, and the multi-particle states actually use some of the features of this algebra. Perhaps more conventionally, we can focus on the standard large Q limit of SYK. So this is just the conventional, without double scaling limit, where we take lambda goes to 0, but hold temperatures fixed. So holding temperatures fixed is equivalent to holding the length of the wormhole fixed, right? So at finite temperatures, the length of the wormhole is held fixed. And that gives us some other thing. Now, this other thing that it gives us is a bit of a surprise. So in particular, just by plugging in the concrete expressions that we have, we get this particular algebra, this particular expression for P, D, and E, which you see are identical to the ones in the previous slide, except for this factor of C. So in particular, we still get the SL2 algebra, even at finite temperatures. And what's interesting is that the only modification is the factor of 1 minus c squared multiplying E, which can be reabsorbed into the definition of E. Okay. This factor of 1 minus c squared is an important thing. So C, remember, is related to the length of the wormhole, and that thing is being held fixed. So this immediately poses 2 questions. So the first question is, we found an SL2 symmetry, but chaos is sub-maximal, so what gives? And second, is there a hyperbolic space on which the symmetry acts as some isometry of that space? Okay. So we're trying to understand now the bulk dual of standard large Q SYK. Is there a sense in which it's still hyperbolic despite being at finite temperatures? So despite being far away, let's say, from the Schwarzschild limit. We could even be talking about nearly infinite time. Okay, so the answer is, in order to answer that, we can work out the action of the generators of the states. We can work out the action of the generators on some particularly special states. So these are states where we inserted a matter operator at some Euclidean time in the past. And in this particular limit, we can evaluate the action of the symmetries by using the fact that the symmetries just involve this length. And this length is computed by the size. And the size, therefore, just gives us the 4-point function. So we just need to know the OTOC in the standard large Q model. And thankfully, that was already computed in various papers. So if we know the OTOC, we can work out the action of the symmetry generators on these boundary states. And what we find is that the answers are quite simple if we introduce something that we call the fake hyperbolic disk. So the fake hyperbolic disk is engineered to reproduce the correct 2-point function of large Q SYK. So in large Q SYK, the answer for the 2-point function is just this factor here. And it looks like the conformal answer, except that you have to rescale time in a certain way. And this hyperbolic disk is designed such that you rescaled the time in the appropriate way to reproduce the 2-point function. So in particular, u equals 0 is here, and beta over 2 is over here. So the total circumference of the state is not beta, but it's something else which has been engineered to get the 2-point function. Okay, so the dash part is in some sense unphysical. But however, when we introduce this picture, the answer that we get for the symmetry generators are quite simple. They act as time reparameterizations of this boundary fake time, okay, phi. And these are just the standard SL2 boundary time reparameterization. Furthermore, we can then compare the action on the boundary with the action in the bulk. Doing so gives us a formula for where x of the particle is as a function of phi. So this was all defined, let's say, from the microscopic theory, right? It was defined in terms of Chord numbers and so forth. We did an honest calculation of this thing, and we found that the answer was reproduced by a hyperbolic geometry calculation where we start with the fake disk, and we demand that the geodesic ends on the slice with a right angle. So that was a bit of a surprise to us. Furthermore, there's some missing region here in this picture, and it seems like we can actually solve the inner product in this particular regime. We find that the inner product has this factor of the global time translation, which exactly accounts, some factor of the inner product accounts for the missing region. Okay, so it seems like the middle region is somehow associated with the inner product, although we don't have a great understanding of that. As a final comment, I will say that the total circumference of the space is exactly matches what we would have expected from the chaos exponent. So the chaos exponent is related to the fake periodicity of this fake space, okay? But all these effects seem to align. So these were all basically discovered experimentally by doing this whole like microscopic algebra stuff, doing a bunch of chord combinatorics. But the output is consistent with this sort of fake hyperbolic disk, where we actually have some negative global Euclidean time evolution. It's quite strange. But maybe the fake disk is not so fake. That's what we're trying to do. Okay, so let me end with a summary. So the chord diagrams can be sliced open in some way to define a bulk Hilbert space. And this bulk Hilbert space is essentially just interpreted as the length. So when you have matter particles at the various locations, you're really building up a Hilbert space by specifying where the matter particles roughly are in the middle of this chord diagram. So I would say that this is as close as it gets to some sort of explicit derivation of holography in admittedly a very toy model. Furthermore, we found that using the chord Hilbert space picture and asking about its symmetries constrains the possible bulk matter, the interpretation of the bulk matter in this theory. So in particular, the bulk matter transforms under this funny quantum deformed version of SL2. So the Hilbert space can be organized into representations of this funny group. And we did not discuss it, but the bulk to boundary map can be made very concrete. So there's some algorithm that you could put into Mathematica. If you tell me you want, some matter particle with some particular state, some particular location in the wormhole, I can put that into Mathematica and tell you some boundary expression for what that's doing. So that's a bulk to boundary reconstruction that works even when the Schwarzian fluctuations are large. They could be small. The Q deformation parameter could be large, it could be small. So it's some very sort of fancy bulk reconstruction. The analog in Super-Yang-Mills would be like doing a bulk reconstruction that includes all stringing corrections, right? So this works well in a regime where the chaos exponent could be quite small. So we're getting perhaps closer to understanding of the bulk dual, and perhaps there are also some general lessons for sub-maximal chaos. Thanks very much.
To learn this from Brian.
Thank you. So we have time for questions.
Could you elaborate on the role that this other Chord algebra structure plays?
Yeah, sure.
You have two particles which transform under SU2. The total angular momentum is the sum of the first angular momentum and the second. So that's true for Lie algebras. It is not true for these quantum groups. So in particular, the tensor product of two quantum groups has this funny fact that you need to do something nonlinear to the analog angular momentum. That thing is called a coproduct. And the coproduct of SL2Q is some well-defined expression in terms of these, in terms of the SL2Q of the first factor and the second factor. Now, when you have two particles in the wormhole, the expressions for these symmetry generators, you can check from the microscopic definition, agree with the Hopf algebra sort of definition, the coproduct. So in other words, you could say that this the symmetries don't act linearly on the matter particles in this quantum group. They don't act linearly on the matter particles. So you can't really say that you translate the first particle and translate the second particle separately. But there is some generalization of that holds, and that's what we know about it. So a little bit more of the Q-deformed structure than just the algebra.
Sorry, I always get confused because this symbol Q gets defined a whole bunch of times. Lost track of it. So if I want to compare this to, like, say n equals 4,
Yes.
So presumably you're at large n, but sort of what values of lambda are we talking about?
Yeah. Okay. Good. So the analogy for infinite n equals 4 Super-Yang-Mills is that we take Q goes to 1, so frac Q goes to 1, lambda goes to 0. Okay. However, we keep the temperature finite. So finite temperature means like keeping the stringy corrections. In the analogy to Super-Yang-Mills, the finite temperature is like the keeping the stringy effects in Super-Yang, because the chaos exponent is finite. But this is still a limit where the theory completely like there's still large n factorization, but there's some sub-maximal chaos. So that's the extent of the analogy. Yeah, big floppy strings, but you see, that's exactly the question which we were trying to understand, which is you don't expect in this limit to have any geometry, any geometrical picture in general, right? A big floppy string. Yeah, but here we seem to find some sort of weird geometry involving this vagueness.
Yes, can you speculate about whether or not this phenomenon happens, say, in n equals 4? Like, for example, the length becoming discrete or something? Or...
I'm not comfortable speculating.
It were true, but
when we consider integrability on the string worksheet, it looks like the length becomes discrete. I don't know if this connected with it. Another question, if I may. So we thought that the SYK model perhaps was not the local theory in the bulk. So suppose you do this and you then find the interactions between the bulk particles and so on.
Yes.
So the question is whether you are indeed finding a local theory.
Yeah, thanks for the question.
I think one subvariant of that question that we tried to address is whether we really get, even in the JT limit, massive fields, let's say massive free fields. So I would say qualitatively, it sounds promising. However, one thing that we're trying to understand in detail is whether you get, for example, a Klein-Gordon norm. So whether the particles, so there's some wave function psi of x, right? And we have some inner product that tells you how to complete the overlap state. And one question we'd like to know whether this inner product has an interpretation of this Klein-Gordon.
From the chord diagram,
Yes.
it's a local amplitude.
Well, the OTOC has been calculated, and it has this funny phase method that's discussed. But the OTOC is not just P times Q, like the gravitational scattering. It's a bit like the stringy expectation values, like I times P Q some power, get some phase factor. So in that sense, there's some sort of non-elastic domain. I don't know how that statement relates to any of these chord discussions.
Right. So that's what these are. But in this limit, the action becomes this local Lorentzian Liouville action. But it's still a local action.
Well,
I don't think that the Liouville action has a clear bulk interpretation.
in terms of, let's say,
Isn't the solution to the Liouville equation precisely the large Q?
Yes, that's correct. But yeah, I don't know. I don't know how to go from. I'm not saying it's impossible, but I personally don't know how to go from say some description, let's say, with some Lagrangian involving massive field. I think the best thing that we know how to do is to do these chord things and use this Hilbert space and compare them with the Hilbert space and get, let's say, 3 particles. That's the thing that I know how to do. It may be possible, I just don't know how to do it.
So your big disk, does it give some geometric explanation of why the energy spectrum is bounded in the scale?
quite
Not immediately. But okay, one thing you can say is what is the period of the disk at very high energies? So at very high energies, it's basically inverse state. Like, but so this fake disk does not go to 0. In some sense, the chaos exponent and so forth, stays finite. And that seems to be related. That's the best that I can do.